So, hello everyone, my name is Ryan Kim and my current school is Choate Rosemary Hall. And may I begin?
Yes, go right ahead.
Hello, my name is Ryan Kim. My project is titled Just a Rather Very Intelligent Traffic System, JARVITS, a novel deep learning IoT traffic control system for real-time detection and signal optimization. My project was inspired by a story I heard while volunteering at my local disability center. One of the patients there had lamented about how he had lost his legs due to not being able to get to the hospital quickly enough, and I was inspired to help him out. In the status quo, traffic control systems operate on predetermined patterns from past data, which makes them unable to adapt to real-time changes. They also often fail to differentiate between the types of vehicles in congestion and control traffic lights independently of one another. And because of these problems, issues such as a reduction in the total throughput of an intersection, long waiting times translating to increased greenhouse gas emissions, which is unhealthy for the human body and for the planet, and increased risk of death for people who are in need of emergency care arises. Therefore, the goal of this project is to develop a system which enables real-time traffic control consisting of an IoT device for vehicle detection and a traffic signal optimizer. So, my research project proposes a simple, portable, and affordable IoT device to detect traffic situations in real time. Secondly, an analytical traffic signal optimizer. Thirdly, a traffic simulator. And fourthly, throughput improvements exceeding 30%. This overall research project can be divided into two key sections. First is the IoT traffic control system, and second is the traffic control optimizer. As shown in this graphic, the IoT traffic control system can be further divided into two subsections. First is a physical system, and second is a vehicle and lane detection algorithm. Together, these systems prove that the IoT device is able to locate and determine a vehicle's lane in real time. Next is the traffic control optimization process. Because real traffic lights cannot be connected to and altered to verify the advancements proposed by my system, a simulation is used instead. The traffic control optimization section is again further divided into three sections. First is traffic simulation notation and explanation. Second is the analytical algorithm optimizer. And third is a traffic simulator and control. Finally, a conclusion and future research agenda are also presented. The physical system looks like this graphic here on the left, and the functional requirements of this system are as follows. First is simultaneous real-time video recording in all four directions. Second is that it's clearly visible to pedestrians and drivers to avoid collisions. And third is that it can be developed affordably, deployed, maintained, and replaced affordably as well. And the components used to develop the physical system include a Samsung USB camera to provide real-time images in all four directions for vehicle and lane detection, a music stand that is light, height adjustable, and can be used as a handle. Third is a traffic cone to encase the whole system, and most importantly is universally understood as a warning system for drivers. Fourth is an Intel NUC PC to run the object detection algorithm and traffic simulation. And fifth is a battery, and sixth is a flashing warning light. For vehicle detection, a custom algorithm was developed from YOLO v3 Tiny, itself a version of the YOLO v3 object detection algorithm, and this is because YOLO v3 Tiny had too high of a computational cost and due to the limitations of the physical hardware system and battery life. So, one of the two 26 by 26 by 26 detection heads was removed because it was optimized for detecting small objects, which is not really relevant when detecting cars. And also 17 additional layers were removed to create a custom lighter and faster algorithm, which was also more accurate. For the lane detection algorithm, the Hoffline transform was used to identify the lanes from which the x-coordinates could be used to compare with the car's bounding boxes to determine which lane a vehicle is in. The dataset I used contained thousands of images, including ones that I had taken myself on the streets, along with images from the internet. Since the IoT hardware traffic controller cannot be connected to an actual traffic light to control congestion, to test the effectiveness of the proposed system, a custom traffic simulation was devised. The simulation looks like this upper left graphic, with one four-way intersection with 3 lanes each. Vehicles in lane 1 can only turn left, while vehicles in lane 2 can only go straight, and vehicles in lane 3 turn right 30% of the time and travel straight otherwise. State matrices N and E are used to describe the current situation, recording the number of normal and emergency vehicles in each direction and in each lane. This data is gathered from the vehicle and lane detection algorithm mentioned earlier. And here, the notation EW2 is defined as the number of vehicles in the second lane on the east side heading west. The graphic below shows 4 vehicle states labeled T1 to T4, which represent the duration of each state. These 4 states combine to last 2 minutes, and the objective of the algorithm is to optimize the values of T1 to T4 to maximize throughput. A custom analytical algorithm was devised to optimize the duration of T1 to T4 to maximize the throughput and minimize waiting time in an intersection using pseudo-optimal logic. The algorithm I devised is used to determine the values of T1 to T4, and this is done by getting the proportions of the number of vehicles in each direction and adding that up to 2 minutes. This algorithm is applied to each of the 4 traffic directions. So you can see the algorithm on the left and its applications to T1 to T4 below that in 4 equations, and can be calculated, and the values of T1 to T4 can be calculated with the equations on the right. You may also notice that the T values are multiplied by 100 and the fraction instead of 120, and that's because each traffic light has 5 seconds of yellow light duration between when it turns red and the next light turns green. Also, a minimum of 10 seconds is allocated to the directions T1 to T3, so when the vehicles are moving that way, and the intention behind that is to enable pedestrians to have enough time to be able to cross the intersection. Instead of using a commercialized simulation, a custom simulator was devised using Pygame to allow for flexibility to expand to future research projects, such as the one I'm currently working on, which involves simulating multiple intersections and kind of controlling traffic lights there. The simulator looks like the image on the left and was devised using a hybrid deterministic stochastic time and using Pygame. The simulator receives T1 to T4 values, the N and E matrices as input, and sets a duration of each traffic signal and generates the required number of vehicles for each lane. And the simulation operates at an accelerated pace. The implementation and the results are as follows. When compared to YOLO v3, my custom detector, despite being faster and smaller, was also more accurate overall. Looking at the table, the reason behind why the car class has such a lower MAP is because it encompassed all vehicles that were not ambulances, so cars, trucks, buses, all the lot. One potential future research area is improving this value by further splitting this down into separate car classes, truck classes, and bus classes. As for the traffic simulation, traffic conditions were simulated from 6 to 10 a.m. in 1-hour intervals, with 6 to 7 at low, 7 to 8 at medium, 8 to 9 at high, and 9 to 10 at medium, reflecting commuting hours. Low was defined as 480 cars an hour, medium 1440, and high was 4320. The first graphic on the furthest left shows throughput over time, with blue showing my optimized method and the orange line showing the predefined fixed method. The second graphic shows the throughput per cycle, and evidently my optimization algorithm provides significantly greater throughput. Therefore, the following future research areas for this project for the vehicle and lane detection algorithm is the fact that the dataset could be improved by increasing the diversity of images and videos used, and as I mentioned earlier, diversifying the car class into car, bus, and truck classes for superior class-based MAP. For the hardware IoT system, the limited battery life could be resolved by installing solar panels, and the IoT device could also be taller to enable a broader view of the intersection. For the simulation, it could be made entirely stochastic and faster still, using event schedulers to skip over events when nothing really happens. And also, as I mentioned earlier, we can model the relationships between several adjacent intersections and then optimize traffic control for all of that. And building off of that for optimization, future research areas are a new scheme to work with this multi-intersection simulation and also addressing various complications that may arise from there. Therefore, the key takeaways from my project is that it's a feasibility study on developing a deep learning IoT traffic control system that analyzes real-time camera footage to detect vehicles and optimize traffic signals to maximize the throughput of an intersection. And this research project presents a novel IoT device, analytical algorithm-based optimizer, and a traffic simulation that together significantly improves throughput in an intersection. Thank you so much.